Hello, my name is Aryan Shenoy, and today I'll be telling you about the hybrid topological neural network, a novel approach to signal segmentation for the optimization of the regenerative peripheral nerve interface. Annually in America, 185,000 Americans suffer from limb loss due to an amputation. And the main avenue of treatment for these patients is prostheses. However, many report that they suffer from a lack of intuitive control, fine motor control, and refined sensory ability. One attempted solution to this is the regenerative peripheral nerve interface developed in 2016 to combat neuroma pain. Due to its construction, however, as you can see in figure 1, in A, you can see the transected peripheral nerve, and B, the myelin muscle graft. In combination with a electrode, it was discovered that this signal system could actually be used to detect neural signals. The device itself preserves muscle function and enables intuitive control. As I've mentioned, it also reduces neuroma pain and offers sensory feedback. In 2020, it was discovered that different regions of the RPNI, as you can see on the left of the figure, correspond to different regions of the hand, as you can see on the right of the figure. Due to this, electrodes placed on the RPNI could actually be used to detect neural muscle impulses and determine motor intent, possibly being used to control a prosthetic device. Looking at the actual construction of the RPNI, specifically in the case of multiple RPNI devices, you can see that a nerve can be segmented into multiple parts and then surrounded by bioamplifying muscle grafts. One advantage to this is electrodes can be placed on each of the RPNI devices and then be used to track exactly which impulse corresponds to which nerve, and then use that to control the device. However, the problem arises is that this surgery is often extremely painful and the rehabilitation is even more so. Many patients do not begin using a prosthetic until 6 months after, which greatly reduces their chance of having a successful rehabilitation. The lab theorizes that this can be mitigated by using a single RPNI device. However, the problem arises with this is that when multiple nerves are in a single RPNI device, due to their proximity, the bioamplifying muscle graft, and the location of the electrode, the the actual nerve where the signals originate from cannot be accurately determined. Modern methods of signal segmentation, such as principal component analysis, independent component analysis, and the wavelet transform, or WT, are all used for signal segmentation of different kinds. However, they have all been proven multiple times, such as by this 2004 study, to have no precedence in neural signal decoding. They all have significant strengths, but again, they all suffer from significant shortcomings, specifically in this use case. And that leads us to the problem for this project. When multiple nerve fibers overlap in a single RPNI device, the nerves that the signals actually originate from cannot be accurately determined, which means a device cannot actually be used in this case. The goal for this project is to create a signal segmentation algorithm that outperforms traditional strategies, achieving an accuracy of greater than 95% and minimizing performance drop-off. Now let's get into what I actually did for this project. It all started with data labeling and pre-processing. All the data was acquired from my mentor's lab over an 8-year period. I divided the data into the 13 classes corresponding to the degrees of freedom within the hand, and then applied a bandpass filter of 1 to 500 hertz to it. The hybrid portion of my project comes from the next step, feature extraction. Standard signal segmentation algorithms only use frequency domain features, often ignoring time domain features completely, which creates temporal inaccuracies, which is not beneficial for a prosthetic use case. For the time domain features, I use mean absolute value, root mean square error, and zero crossing rate to determine these features. In the frequency domain, I use power spectral density and dominant frequency components to gather these features. The next step was topological data analysis, which is where the topological portion of my project came in. This starts with point cloud construction, which involves taking all of the data gathered in the previous step and putting it into a higher dimension point cloud. After this, principal component analysis, is used to reduce the dimensions of this multiple dimension point cloud. It basically works by creating vectors within this point cloud and reducing the overall number of data points, which in turn reduces the actual dimensionality of the system. Then simple complex construction is applied to the system. Basically, how this works is it takes all the vectors and creates areas within the point cloud. And these areas can then be used in persistent homology to determine exactly which class each data point corresponds to. The final portion of this is the neural network architecture. I use 32 filters with a conv1D, max pooling of size 2, dense of 128 units, and rectified linear learning unit, and an output of the 13 classes with a softmax activation function. Now let's look at what we actually found. Looking at the amplitude-based metrics, you can see that the actual signal in blue and the predicted signal in red had a high degree of overlap. It is actually determined that they only had a 0.02 deviation, which was far greater than what we were looking for. In the time-dependent metrics, you can see the CNN red benchmark and the blue HTNN test. The benchmark suffered a lot with temporal accuracy, whereas the HTNN had a high degree of temporal accuracy, achieving 99.7% accuracy. Looking at the TDA, you can see on the left with the persistence diagram that all the data points were well above the line, basically meaning that all of the simple complexes constructed were very accurate to what we were actually looking for, and no high dimension spaces were created that were unnecessary. And looking at the Betty numbers, you can see that the average was 4.9, which is well above what we were actually looking for. The baseline for most of these systems is actually only 2.7. And finally, for the performance-based metrics, you can see that the power utilized by the system is very, very low, and actually it only incurred an onset latency of 2.1 milliseconds. AMG classes. The layer contribution was specifically interesting in the study. It showed that deeper HDNN layers enhance signal feature isolation, which was unique to the study. In all my previous work, I've only seen feature activation within the first few layers. Frequency performance in the mid-range was actually much improved, and the noise impact was significant in the study. Specific ranges of noise actually increased the model's classification accuracy, which was particularly interesting. And just to wrap everything up, the problem for this project was that overlapping nerves inhibit high fidelity detection of independent control signals. The goal of this project was to develop a signal segmentation algorithm that achieves an accuracy of greater than 95% and does not compromise performance. To do this, we used topological data analysis and dual feature input combined with machine learning techniques. In the end, we achieved a temporal accuracy of 99.7%, a minimal amplitude error of 0.02, and an onset latency of only 2.1 milliseconds, which is insignificant in the scale of neural signal decoding. This project is very important. Around the world, over 57.7 million amputees suffer from limb loss. Over 50% of prosthetics are actually abandoned because of a lack of fine motor control and lack of intuitive control, which leads to frustration. The HTNN offers a high-fidelity solution with real-time adaptability while also reducing pain and recovery for patients. In the future, I want to integrate the HTNN into real patient systems to validate its effectiveness. I want to expand datasets for broader HTNN generability, looking at different prosthetics, as this study was specifically geared towards upper limb amputations. And I also want to explore HTNN use cases in surface electromyography prosthetics, which is also just a different method of detection, whereas RPNI are innervated, these are surface electrodes. My name is Aryan Shenoy, and thank you for listening to my presentation.